Thank you very much. Thanks, Boumediene, for the invitation. I have to admit that I'm dynamical system person only, but I got at least a little bit involved in recent years in data analysis via topological data analysis. And the talk which I want to present today is a project which started a year ago together with Herbert Elders-Brunner and also his two postdoc, Michał Lipiński, my former PhD student, and Manuel Soriano Trigueros also joined this project. So part of the results will be based on this extended collaboration. So dynamic look at the persistent homology. Here is a very brief recall from, I think, the first Herbert's paper where he introduced that idea of persistent homology. Very briefly, the idea is that you keep building a simplicial complex by adding simplex by simplex, as in this example. And then in this course, the homology generators appear and disappear. And the observation of Herbert and his co-authors, Lectures and Mrozek, in that paper was that actually every time you add a simplex, either you generate you produce a homology generator or you kill a homology generator. There are no other options. And this way, there is even more. You can associate the homology generator to the birth time, to the simplex which gives its birth, and to a simplex which gave it death. This way, they produce this pairing of birth-death pairing, which became just the main tool in one of the main tools in the present day topological data analysis. Why? Because, okay, so maybe this is a kind of summary or just the message I want to present, which was a kind of surprise both to me and to Herbert, that a filter, this is what was called in their paper a filter, this sequence of, sorry, I'm used to my slide changer, which operates slightly differently. I have to learn, sorry. So this sequence of simplices is just a filter. The only condition is that you cannot add a simplex before you added all its faces. So this is the only condition for a filter. And the main message of my talk is that actually a filter may be viewed as a combinatorial Morse function. And since you have a Morse function, so like in the classical Conley theory, this Morse function induces a combinatorial dynamical system. And once you have this dynamical system, you can look at these dynamical systems via available topological tools. And this extra information strongly enhances the persistent diagram information as a tool in the topological data analysis. What is this persistence diagram? This is this pairing, birth-death pairing. So each, when you go through the filter, each time you encounter a cell, you either generate or kill a generator, then you get this pairing, you mark this as birth-death pair on the plane, and you get this topological image of the construction of the space. This is what they use in the image analysis, shape analysis in TDA. Okay, so for those who haven't heard earlier about persistent homology and maybe are familiar with this concept widely used in mountaineering, this is almost the same as the idea of prominence. Prominence is what mountaineers use to judge how important a mountain is. And the naive definition, but intuitive definition of prominence is that if you are at the top of the mountain, then the question is how far you have to go down in order to reach a higher mountain. And so, for instance, for this mountain, the prominence, you just have to go down here. So this is the prominence, and then you can go up here. But for this mountain, actually, you have to go much farther here in order to be able to reach a higher mountain. So this pairing of the mountain and the pass, because you have to reach a pass going down, this pairing between mountain and path is like this birth-death pairing of homology classes. So here is an example. Everything here will be based on a very simple example. My space is just a circle, a very simple one. But let me emphasize, all what we do is dimension independent. The example is one dimensional to keep things simple. So my space is a circle. It's triangulated via vertices and edges. And I add them in this order. So I start with vertex A, G, C, B, then I add edge B, C, and so on. So the order of adding the simplices is marked here with the numbers. And then you produce this pairing, Berdiev pairing. So this is the classical persistence diagram. Each dot tells us, for instance, this one, that there was a homology class born as when you added, I guess, the 5th simplex, and this homology class was killed by adding the 10th simplex in the sequence. And here is also this pairing of simplices. So actually, BBC, it means that when you added B, a homology class was generated. This was just connected components, nothing else might be interesting in this one-dimensional example. But after adding edge BC, this connected component would join another one, so it disappeared. But of course, okay, here is an example that actually the edge which kills a connected component need not be directly connected to the vertex which gave birth to this connected component. But let's look at this height. So just try to think about it as in this image with these mountains. So a sequence is just a map from integers to, this filter is a map, a sequence of simplices which assigns to integer a simplex. But this is an injective map. You can invert it. So you can think about this as a map from the collection of simplices to integers. So this is a real valued function. And actually, there is even slightly more definition of a filter. It's just an injective function. The values need not be integers, maybe reals. And the only condition is if t is a phase of S, then the value at t must be strongly less than the value of S. So with such a filter, you can treat such a filter actually as a Morse function. And this is the same example, but I just, to be able to draw the graph, I cut the circle into an interval from A to I, but I is identified with A, so it's still a circle. And for every cell, I marked here the moment it was added to the filter, and they had smoothed this for a better interpretation. But everything is here combinatorial. This smoothing is only to guide the intuition. Because actually the intuition I suggest here is to think about this as a mountain range in the winter and populated by skiers, and ask yourself the question, what is the geometry of this mountain from the point of view of a skier? Imagine we have a skier at the top of this mountain. If this is a downhill skier, not cross-country skier, then there are only two options: go down here to this valley or go down here to this valley, and then the journey ends. So in order to increase the options for the skier, we can build ski lifts. And the ski lifts, we can build them in an efficient way using the following rule. Namely, for each mountain, we can look the nearby valleys and find the one which is the highest one, so that the distance will be small. But do the same from the point of view of the valley. And when we see a match, so if this is best choice both for the valley and the mountain, then we build the lift. So in this example, these lifts would be located at these places, marked by these arrows. And the point is that from the point of the skier, the geometry changes. Namely, think about the same skier at the top of this mountain. Now she can reach, for instance, even this valley, because she can take these lifts. But she cannot still reach valley A. This is still an obstacle. So what's going on interestingly here? First of all, when we go back just to pure combinatorially algebraic look, we can look at the boundary operator. So here are our vertices and edges. The boundary operator here is very simple. The boundary of a vertex is 0, so the columns for vertices are 0. The columns for edges have 2 ones, just 2 endpoints. And of course, when you go back here, the lifts go always from a valley. Valley is represented by a vertex, a mountain is represented by an edge. So it's always from the vertex to an edge, the lift, but not everywhere, only at some places. They are marked, our lifts are marked here with this pink color. So this means that we have a lift from B to the mountain BC. But to make it more formal, I give the following definition. So a facet pair is just a pair where T is a facet of S. A facet is a face of codimension 1. And I say that a facet pair is shallow if it satisfies the following 2 conditions. T is the latest facet of S in this ordering, and at the same time, S is the earliest cofacet of T in this ordering. You can use also this Morse function, this height. So T is the highest, lowest in this matrix, because the ordering here in the matrix goes from the top to the bottom, but actually AB is the highest mountain here. Oh, sorry, this is not, again not this direction. Yes, the AB is the highest mountain. So in this matrix is at the very bottom. Okay, so this concept of shallow actually has nice features of shallow pair. First of all, every shallow pair is a birth pair in the sense of Edels-Brunner persistent homology. Then any 2 different shallow pairs are disjoint. So a shallow pair cannot have a common vertex or common edge with another shallow pair. And the family of doubletons consisting of shallow pairs and siglets consisting of cells not in a shallow pair forms a gradient combinatorial vector field in the sense of Forman. So here I have no time to go into this, but there is this version of Morse theory proposed by Robin Forman at the very end of 20th century, which shows that actually given just a simplicial complex and a Morse function properly defined in his papers, you can produce a combinatorial analog of a dynamical system, and it's gradient, and you can prove the fundamental theorem of Morse theory, that the critical cells in this combinatorial version, the number of them is in greater or equal than the Betti numbers of the simplex. And this is done via a dynamical system. So in classical Morse theory, there is this gradient vector field producing a gradient dynamical system. Here is this combinatorial analog. So we'll use these shallow pairs to build such a system. And going back to our example, I said that every shallow pair is a birth-depth pair, but not vice versa. We have altogether here 7 birth-depth pairs, but only 5 shallow pairs. So 2 are not shallow. This CDE is not shallow, and GHI, this is also birth-depth pair, which is not shallow. So there is a natural question, what is the relation? Why only some, every shallow is birth-depth pair, but not vice versa? Can we regain the other ones? And here is the answer, an interesting one. So first of all, this is a very brief idea about this dynamical system. So again, back to our circle. These shallow pairs are marked as these vectors. So there is a lift from D, valley D to mountain CD, all other lifts. And this gives you a kind of dynamics as the skier, how you can go. And there are critical cells. The DE, this mountain does not belong to a pair. There is also A, which does not belong to a pair, a few of them. So these are these critical cells which correspond to critical points in classical Morse theory. And there is one other way of interpreting this change of geometry. One is via the skier, but the other is via a kind of homotopy, so that you just squeeze this edge EF from E towards F, then you squeeze FG from F towards G, also in this direction, so the outcome is that actually now this edge DE stretches from C to G. This is a new cellular decomposition of the simplicial complex. Maybe I skip this. This is a two-dimensional version. Let's stick to this one-dimensional for this talk. So this change of geometry may be also viewed as a kind of flattening some valleys and mountains. This, of course, in reality would be much more expensive, but it also is good to guide the intuition. So you may look at it even this way. So this is after the change of geometry. So we rebuilt our mountains. We have new mountains, new valleys, less of them, and we can iterate the process. We can ask again about shallow pairs. This is a new Morse function on new simplicial complex, new division of the circle. And there is only one shallow pair in this case. So you make this squeezing of this shallow pair and you get another one, again a shallow pair, and you end up with a Morse function which is a perfect Morse function. So the number of critical cells now is in one-to-one correspondence to the number of cells in this cellular decomposition of the circle. This is a cellular decomposition which consists of one vertex and one edge. So this is not a regular cellular decomposition, but still a cellular decomposition. And the point is that you saw that we missed two Berdiev pairs. Actually, this is where we regained them. So there two were missing, and one is, so it is the, something is now, no, it's not my mistake. Okay. So this is the pair C-CG, but in the original, so CG came from extending DE. So this is this pairing C-DE, which shows up here, and then GHI shows up here. And actually, this is not a coincidence. This is a theorem. I showed this theorem, but there is one important observation here, that the question is, can we do always this homotopy? It's so nice on this simple example, and in general, it's known that perfect Morse functions are not always possible. There are obstacles, and the simplest case, which is known to be such an obstacle, is a Duns head. So a Duns head, a triangle in which you identify the edges according to A glued to A, B glued to B. This is a filter, and when you do the same, you look for the shallow pairs here. So here are the shallow pairs. When you do all the squeezing here in this example, you end up in the standard representation of the Duns head, and this one is no longer regular, and since it's not regular, these homotopies are no longer possible. So this is when you stop, when you really want to do actual homotopies. But the point is that when you do it purely algebraically by using the concept of complex introduced by Lefschetz in his 1942 book, you can think about a Lefschetz complex as an abstraction of a cellular complex, algebraic abstraction of a cellular complex. Some people say Lefschetz complex is just a base change complex, so a chain complex in which a base is fixed. But it's better to think that the main object is just the base, and the chain complex should be considered to be on top of it anyway. So the point is that when you do, when you work with Lefschetz complexes, the concept of filter still makes sense, because you have these basis elements. You can order these basis elements. There is the concept of facet still possible, and in the setting it is almost algebraic, but with this small flavor of geometry, which is still present in the Lefschetz complex. You can do all these cancellations to the very end, so that we can prove the following theorem. We'll skip, I have no time to go through the details of the definition of the Lefschetz complex. So think about this as an algebraic abstraction of cellular complex. The point is that we have the following theorem. So first notation, given a filter, as I already defined, this is the set of all birth-depth pairs associated with the filter, and this is the set of all shallow pairs associated with the filter. Then we can prove that a filter which is not boundaryless, which means that there is at least one facet of a face, admits at least one shallow pair. This is not so difficult to prove. Much harder is prove the following, that if you have a shallow pair, and then you do the cancellation, this algebraic analog of homotopy, or chain homotopy, you get a new filter on the, so you just remove this shallow pair, you get a new Lefschetz complex. That's a standard earlier theorem, that such a cancellation still leads to a Lefschetz complex. You restrict to the new Lefschetz complex your filter, and you prove that this is still a filter. And the most important thing is this feature, that the birth-depth pairs of the original filter split as the birth-depth pairs of the new filter plus the one shallow pair you extracted from it. And the consequence of this is that actually you can introduce the sequence of derived filters, and then your original birth-depth, the set of birth-depth pairs splits as a disjoint union of these shallow pairs of these derived filters. And this stops. So there is such a k, there exists an integer k such that this k minus first filter still has shallow pair, but the kth filter is already boundaryless. So the Lefschetz complex for this kth filter is boundaryless. So there is no need to iterate because there is no more shallow pairs present. And using this theorem, you can actually enhance the concept. Namely, you can introduce the idea of cancelable order of birth-depth pairs. This, when you take all shallow pairs, cancel them, again all shallow pairs, cancel them. This is the one way of doing the cancellation. But sometimes it's possible that there is no need to cancel all shallow pairs. You can cancel only some of them, and already some other birth-depth pairs become shallow. So there are many orders which are cancelable. And actually, when you take the intersection of all such cancelable orderings, you get a partial order, which we call depth poset. So in our example, back to this example, the depth poset looks like this. So these are the original shallow pairs. When you cancel all of them, these two, this one becomes shallow. When you cancel this one becomes shallow. So the third derived filter is already trivial. You need two derived filters to get all this, what one could call this a kind of spectral decomposition. And the point is that this actually enhances the concept of depth poset. So here is an example of three very simple filters on simplicial complexes. So the numbers give you the ordering in which you add the simplices. They have exactly the same persistence diagram. They are at the bottom, and typically the persistence diagram is drawn as here, as a collection of dots. So if you forget about these lines, the collection of dots is the same for each example. But when you mark the depth poset by drawing a line for something which is higher to something which is lower, and this is the direction to the diagonal, from the left of the diagonal towards the diagonal, this is the way you mark depth poset. The depth poset in all these three examples is different. And Michał Lipiński works now, he's now at IST, as I said, working as Herbert's postdoc. He works with some geologists there, and it seems they really have concrete examples showing the difference, that it really matters to look at this depth poset from practical point of view. So they give more information than what people use so far in terms of the persistence diagram. But this is still very early. Another example in dimension 1. And actually, back to the Duns head. So when you just try to do when you try to do the actual homotopies, you are stuck with a triangle. But when you do the algebraic version, you get the decomposition, and you need two derived filters to get the zero version. And we call a filter flat if its depth poset is just identity. We rarely think about identities as a partial order, but it may happen that this depth poset is just collection of points, identity. And this conjecture actually is already proved that Danskhet does not admit a regular serial decomposition with a flat filter. This is quite interesting because this gives a kind of purely homological characterization of the differences between Danskhet and a point. From the classical homology point of view, Danskhet has just the homology of a point. So my time is over. Maybe I just stop here. Thank you. Thank you for your attention.
Thank you very much.